Welcome to the second part of Module 2 of Programming Paradigms CS403. Myself Meenu Matthew. I'm an Assistant Professor in Computer Science and Engineering at Rajagiri School of Engineering and Technology. In this lecture, we'll be discussing what are composite data types. We have seen the primitive or the scalar types in the previous lecture. The composite type is also called non-scalar types. It is created by applying the constructor to one or more similar types, and the examples are records, variants, arrays, sets, pointers, lists, and files. Records and variants. Records are popularly called structures, and variants are popularly known by the name unions. In both structure and union, we store data of heterogeneous type into a single unit, and we manipulate individual items using dot notation. So multiple heterogeneous types can be stored as a single unit. It is called a structure in C, C++, and Lisp. Now in C, we can declare a structure, then the structure name is element. It has four components or four members, a char variable, int variable, double variable, and a bool variable. All are heterogeneous, and it is stored as a single unit called element. To access each individual component, we can use element dot name, element dot atomic number, element dot atomic weight, element dot metallic. Okay, that is the way we access. So in Pascal, the same thing is represented as this. This is the representation in Pascal. The same name, atomic number, atomic weight, and metallic. This is a memory layout for records and variants. This is the memory layout for the structure element with four members: name, atomic number, atomic weight, and metallic. The taken example is a 32-bit machine where each word is 4 bytes. In our case, the first component is name, which takes only 2 bytes. So the first word 4 bytes is divided into 2, and the first 2 bytes is occupied by name, and the rest 2 is a whole. And the second member, atomic number, begins at the second word. It takes 4 bytes. And atomic weight is double data type, and it takes 2 words. Okay, and it takes 8 bytes in total. And metallic is a boolean variable. It takes only 1 byte, and the rest of the 4 bytes, that is 3 bytes, is a whole. How to manage holes or the unused space that we have seen in the previous diagram. The memory layout can be packed together so that the holes are completely avoided. That will give you an arrangement like this. The problem is with accessing. That is, the first word contains name as a whole and half of atomic number. And atomic weight starts at the middle of the second word and ends at the middle of the fourth word. So it is very difficult for accessing, but it avoids holes as such. And in the second rearrangement, we minimize holes by sorting the fields. That is, name, metallic. These two are the smallest among the components, and it is kept at the beginning. And the whole is minimized to 1 byte. Atomic number and atomic weight is the same as in the first diagram. An advancement to records, a nested record. The structure OR contains the member name with another member as a structure of element type, element yielded. Okay, it has 4 members as such. So it is a structure or a record within another record. There is another alternate way of stating this. Char name 30 and struct element can be declared earlier than struct OR, and you can create an object of it. Okay, and for further reference, you can see the use of with statement in Pascal for the use of nested record. Variant records or unions. If you are sure that the member components will not occur at the same time, the same memory space can be utilized by multiple members at different times. Now, such a kind of data type is called a variant record, or commonly called unions. Unions have two main purposes. It is commonly used in the system programs where the same set of bytes can be interpreted in different ways at different times. The space is utilized to the maximum, and it can be used to represent alternate sets of fields within a record. In the given example, there are three components: int, double and bool. In this particular case, we allocate memory such that the memory for the maximum or the largest data type is given to the union, and int and bool can utilize that space at different times. The next composite data type is array. An array is called a composite data type because it is created by applying the constructor onto the primitive data type like integer, char, etc. And I can say that array is a mapping from index type to component or element type. That is, there will be a homogeneous set of elements designated as an array, and we use an index to point to the individual elements of the array. And I use the term homogeneous because we use only data of the same type inside a single array. And in some languages, the index that is used for addressing each individual element is an integer, and in some others they use other discrete types. And scripting languages allow non-discrete index type, and this results in an associative array, and it is implemented using a hash table. This slide shows the array declarations and accessing of individual elements of an array. We are very familiar with the declarations and accessing in C. So here we are declaring an array upper with 26 characters, and each position holds a char. Okay, and in Fortran, to declare the same thing, it is declared as char dimension index from 1 to 26, and the name is upper. The shorthand version of the same thing is char 26 upper. Okay, and in Pascal we write var upper array A to Z of char. Then accessing individual elements. For example, if you want to access the third element of an array A, in C and Pascal we use A of 3, where 3 is within square braces, and in Fortran and Ada we use the 3 within simple braces. Dimensions, bounds and allocations. The first one is global lifetime and static shape. From the name itself, it is understood that the shape of the array is static, meaning it is known at compile time. So, and if the array can exist throughout the program, then the compiler can allocate space for the array at compile time in the static global memory. Then local lifetime and static shape. The shape is static, but the variable is, or the array is confined to a particular subroutine. In that case, the space is allocated in the subroutine's stack frame. I hope you remember the stack frame from module 1. That is, this particular array is used only in that subroutine, so its space is allocated in that stack frame. Then local lifetime, that is, it is local to the subroutine, but the shape is known only at the elaboration time or runtime. That is the third type. DOP vectors. For statically non-dimension and bounds, during compilation itself, the array bounds will be stored in the symbol table. For the use of an array in the program, we just have to look up the symbol table to get the dimensions and bounds. What if it is not statically known? Okay, this is a case where we use a DOP vector. The DOP vector will contain the lower bound of each dimension and the size of each dimension other than the last. In order to avoid redundancy, we do not store the size of the last one. It can be found out using the offset for each field. Stack allocation of arrays. Now, before we see the stack allocation, let me introduce another array which is called the conformant array. The conformant array is nothing but an array in which the upper and lower bounds are usually represented as symbolic names, like lower and upper here. You can see in the example, instead of 1 to 100 or 1 to 10, we use symbolic names. And it is highly used in scientific applications like linear algebra and solving a system of equations. Now let's look at the stack allocation of arrays. In the given example, here is an adder program which has a procedure foo, which takes an argument size, and the size is known only at the elaboration time. Okay, So there are two types of objects in a program. The one in which the size is known statically, and the other one is known only at the elaboration time or runtime. So all the objects whose size is known in prior goes to the fixed size. Okay, and all those objects whose size is not known at the compile time is given to the variable size part. Okay, so there are two parts, fixed size and variable size part in the frame, and those items which we place in the variable part will have the a pointer in the fixed size part, and the dot vector is also given in the fixed size part. We just saw the stack allocation for array. Now we'll see what is the heap allocation for array. Now why do we need a heap allocation for array? And if you remember, we use a heap when the memory allocation is dynamic. So array becomes dynamic when its shape changes at runtime. Okay, so for fully dynamic arrays, a stack allocation will not work. Instead, we need a heap allocation. Okay, so several languages including Snowball, Icon and other scripting languages allow the string to change size after compile time. And this is an example where S is a string, it is short, and during execution, during runtime, S is concatenated with but sweet. So it has become longer, the array has become longer. Now S refers to the new string after concatenation. So if the dimensions were known statically, the dot vector could be kept and a pointer to the data could be stored in the stack frame like we saw in the last slide. But since the dimensions change, the dot vector has to be placed at the beginning of the heap block because it can grow or shrink. Array layouts. There are two layouts for an array, the row major and the column major order. Both these are quite familiar to us, but we have a tendency to go with the row major order, wherein the first row will be processed first, followed by the second, then the third, then the fourth, it goes on. But in case of Fortran, they have a practice of going in the column major order. And the whole thing that matters is the loop that is used for traversing the array. And in the picture you can see the row major order and the column major order, that is first column followed by the second, third, etc. And since the row major order is very common, I've put the column major order example in the figure. This is from Fortran. Here we use columns as the outer loop and row as the inner loop, so that we traverse one column first followed by the second. Strategies for array layouts. There are two layout strategies for arrays. First one is continuous elements and the second one is row pointers. A row pointer is an option that is available in C, wherein the rows can be put anywhere. So a machine which supports big arrays can use this particular strategy in order to avoid the segmentation problems. We'll see how in the next slide. Now this is good for matrices whose rows are of different lengths. For example, a two-dimensional array stores a set of strings. Okay, not all the strings will be of the same size. There will be extra spaces in each and every row. For a machine that supports row pointer strategy, this segmentation can be avoided. And the disadvantage is that it requires an extra space for all the pointers. As we have already seen, there are two different strategies for allocation, continuous and row pointers. This is the example for it. We are declaring a two-dimensional array days with the days of the week, and we'll see how is it allocated using the two strategies. Using continuous array allocation, the days of the week are allocated to continuous locations, and the slash represents the end of the string and the shaded region represents holes. Those memory locations are unused. And on the right side you can see the same declaration in a different manner, where there are pointers to each and every row. This is how it is said that a row can begin anywhere in the memory location. You just need to keep a row pointer to show that this is the beginning or the starting address of each string in the matrix or in the two-dimensional array. the advantage is that the holes can be avoided. We saw single dimensional arrays and 2D arrays. Now we'll see what are multi-dimensional arrays. A multi-dimensional array is an array with more than one level. So a two-dimensional array itself is a multi-dimensional array. So a two-dimensional array is an array of arrays. And a three-dimensional array becomes an array of arrays. Okay, don't be confused. It just means you have multiple dimensions. Okay, so these the examples given in the slide is how the multi-dimensional arrays are declared in various languages. The multiple dimensions are declared with the particular data type. Okay, this is how it goes. Moving on to another type of composite data type, sets. A set is an unordered collection of an arbitrary number of distinct values of a common type. Okay, it can have any number of values, distinct values, but all the values should be of the same type. It can be either all numbers or all characters. Now this concept was first introduced in Pascal, and the operations that could be performed on a set are membership, insertion, deletion, union, intersection, and difference. Now Python also supports a set of arbitrary type, but Ada does not support sets. The implementation of set is done using arrays, trees, or hash tables. And on the right side you can see three variables A, B, and C declared as a set of characters. Now A assigns the value B plus C implies all the values that are there in B and C. It is a union operation. Whereas A assigns the value B minus C means all the values that are there in B but not in C. Then A assigns a value B in intersection C, that is all the values that are common to B and C. Okay, these are some of the operations that are allowed in sets. Pointers and recursive types. As we all know, pointer is a reference to some object. Okay, and recursive type means it is recursive or it calls itself. That is, it has to point to an object of its own type. So the recursive data type makes use of the concept of pointers to get it implemented. So a recursive type is one whose objects may contain one or more references to other objects of the same type. And most of the recursive types are records because it contains data as well as a pointer to its own type. So the member fields of the record are heterogeneous. And recursive data types are used, recursive data types are used to build linked data structures like list and trees. And the language that uses recursive type values requires the notion of pointers to point to the object of its own type. And pointer was introduced in PLI. Operations on pointers. The first operation on pointer is allocation and deallocation of objects in the heap, and the second one is dereferencing of pointers to access the actual object which they point to, and the third one is assignment of one pointer into another provided they are compatible. And the given example shows the sample tree where there are explicit pointers to the left and right subtrees, and if it does not have a left and right subtree, it is set to null. And the implementation of a tree, the abstract tree that is given on the left side in ML is given on the right. That is, it points to the left and right subtrees, but if it points to null or if it is an empty pointer, it points to the empty node. Now let's look at some of the examples of pointers and arrays in C. Int star A is equivalent to declaring an array. Int star star A is equivalent to declaring a row of pointers to int. Okay, and such equivalences hold, but there are exceptions. If the dimension of the first type, the size of the first dimension is mentioned, then we allocate an array, else we allocate a pointer. Now let's look at an example. Int n, int star A, int b of 10, a equal to b. Now what happens? Int star A is actually declaration of an array. So n equal to a of 3 and n equal to star a plus 3. Both are equivalent. Why? They refer to the third element, or rather the fourth element of the array A. Okay, you can refer to it either using the pointer or using the usual array representation. Explicit storage reclamation. When heap allocated object is no longer live, the space occupied by the object has to be freed, or it has to be reclaimed. Now, the programming languages like Pascal, C and C++ requires the programmer to explicitly state in the program that this object is no longer live and it has to be freed. The commands used for the same are delete my pointer in Pascal, free my pointer in C, and delete space my pointer in C++. There is an additional functionality in C++ which is called the destructor, which destructs the space taken by an object. And there is another terminology called a dangling reference, which is pointing to a memory location that is no longer a valid object. This is a side effect of storage reclamation. Let's look at an example from Lisp. Here a list is being processed using different functions, list manipulation functions. Let's see one by one. The first one is CAR on a list. Okay, it will return the first element of the list. So the return value would be A. Then CDR returns a list without the first element. So it will return B, C, D, E, F. Okay. And the next one is counts. It will take two arguments, an element and a list, and returns a list with the element inserted at the first place. So A, B, C is the result. Then list. List takes any number of arguments and returns a list with the arguments as member elements. So list has arguments A, B, C, E, F. So it will return A, B, C, E, F as the result. Then append. It merges two or more lists into one. So here that you can see multiple lists and it is all merged together into one. Then the next one is last. It returns a list containing only the last element. Here you can see the last element of the list is EF together. So it will return the last element as EF. Then the last one is reverse. It takes a list and returns a list with the top elements in reverse order. It will reverse the list. Okay, and member is another function which is not given here. It takes two arguments and the second one must be a list, and if the first argument is a member of the second argument, it returns the remainder of the list beginning with the first argument. Files and input and output. Now input-output facility for a system will allow the program to communicate with the outside world. It might be through the input and output devices or it can be with files. Okay, you can write into a file, you can read from a file. The interactive I/O generally implies communication with human users or physical devices. As I already said, the files generally refer to an offline storage implemented by the operating system, and the files may refer to a temporary storage or a persistent storage. Our last topic is equality testing, that is to check whether two objects are equal. Now equality testing has to be viewed in different perspectives. Okay, we can either say equality based on shallow comparison or deep comparison. So shallow comparison is when we refer to the same object. Okay, it is quite easier, but whereas the deep comparison is to see whether two objects are equal in all aspects. So in case of deep comparisons, we have to go into detail as to the left values and the right values of the object. So in case of primitive data types, it is quite easier. We go for the shallow comparison, and for the complicated data types, we need the deep comparison. There are two models for equality. The first one is reference model of variables and the second one is value model of variables. Under reference model of variables, an assignment like A equal to B will make A refer to the object to which B refers. and a deep assignment will create a copy and B will refer to the copy. And under the value model of variables, a shallow assignment will copy the value of B into A, but if the value that has to be copied is a pointer, then the object to which the pointer will refer will not be copied. So most of the languages go with the shallow comparisons and the shallow assignment. The one area where the deep assignment is used or the deep comparison is used is the distributed computing and parameter passing in remote procedure call. This is an example from the language scheme which has three general purpose equality testing functions: EQ, EQV and equal. The first two, EQ and EQV, will compare the syntax and semantics of A and B, that is whether A and B refer to the same object and whether A and B are semantically equivalent. It is a form of shallow comparison. Whereas the last one, equal AB, will see whether A and B have the same recursive structure as well. So the last one, equal AB, is a deep comparison. Thank you for your patient listening. This is the end of Module 2. All the references are from Programming Paradigms by Scott. You can refer the textbook as well. We'll see you in another presentation.